So in this lesson, we're going to look at the function called the reciprocal function. This is the most simple form, really, of a rational function. So we'll look at the family of reciprocal functions. And here's what we're going to do with them. The first objective is be able to sketch the graph of the parent function for that family of reciprocal functions. What does that look like? What are the key elements? And then the second is that we're going to be able to apply transformations to the graph of that parent function. So this part will look familiar. We've done this before with other functions this year, with linear, quadratic, exponential functions, radical functions, and the transformations. I'm sure by now you're starting to have some familiarity with these, things like stretch and shrink, reflection, horizontal and vertical translations. All right, so what is the reciprocal function? It's the function that models inverse variation that belong to the family whose parents is the reciprocal function. Okay, so the previous lesson, right, we looked at inverse variation, and the standard form for that is what's shown here, y equals 1 over x. And in this case, our constant of variation defaults to a value of 1. Now, x cannot be equal to 0. We know why, right? We cannot divide by 0. We get an undefined condition in the function. So what does the graph of this actually look like? Well, we could plug some values in for x and see what we get for y and graph those. So I'm going to do those fairly quickly here, right? If we were to plug in all these values, some of them are a little tricky since they're fractions, and then plot those, here's what we would get. Now notice we actually get two separate graphs. We have a set of values that are negative x and negative y on the left side of the y-axis, and we have a set of values that are positive on the right side of the y-axis. Right? So if you remember in exponential functions, right, we introduced this concept of an asymptote. In a reciprocal function, it turns out we have two asymptotes. Both the x and the y-axis are asymptotes. Remember, asymptote is a value or a line on a graph that the function will come very close to, but never actually equal. Right? So we would have an asymptote along the x-axis, shown here in blue, and a vertical asymptote shown on the y-axis. Okay, so that's the first key point here. Our reciprocal function is going to have two asymptotes. For the parent function, they will both be on the x and y axes. Now, why is the y-axis an asymptote? Because remember, if we keep the condition where x cannot be equal to 0, we get an undefined condition, right? As x approaches 0, we divide by a smaller and smaller value. We get a larger and larger value of y, but x can never actually equal to 0. So that's why we have an asymptote at x equals 0, which is the y-axis. Now, the other thing we already talked about, notice we have two distinct graphs here. We're going to give those a name. We're going to call those branches. So we have two branches and two asymptotes for the reciprocal function. Now, when we're sketching these, we're not going to figure out a bunch of x and y values and plot lots of points here. We're really just going to be concerned about 2 points to be able to sketch these two branches along with the asymptotes. And those points are 1, 1. So you see that kind of flashing on the quadrant 1 up here. And -1, -1, right? If we put 1 in for x, we get 1. If we put -1 in for x, we get -1. So those are really the 2 points that we need to concern ourselves with to be able to sketch the reciprocal function. Now, what I showed you is considered the parent function, right? It's the most simple form. But we can create a family of reciprocal functions by applying the different transformations. So notice we have our a value, we have our h value, we have our k value, the same variables, or really constants, in a function that describe the transformation. So what do they do? Let's step through this. So a does the same thing it did with our previous functions. If the absolute value is greater than 1, it will stretch. If it's less than 1, it will shrink. If it's negative, we're going to reflect the branches in the reciprocal function. H is horizontal, and again, the default is that the form of the equation has a subtraction in it, so we're going to have to think opposite in terms of what direction we move here. And then the K is our vertical translation, so we simply go by the sign. If it's positive, we move up. If it's negative, we move down. Okay, but these are the same transformations. They're just going to look a little different applied to our reciprocal function. All right, so let's look at an example here, okay? Parent function is y equals 1 over x. So the first thing we're going to do is put in those 2 points, right? 1, 1, and -1, -1, and sketch in what the parent function would look like. Now, our a value in this case is 4. So that's going to stretch. Now, what does a stretch actually look like? It's a little bit different than what we've seen with other functions. Think of it this way. Since a really has become our k value, the product of x and y has to be equal to 4, right? We're just rearranging that reciprocal function to solve for our k value, or 4 in this case, which is also we're calling a. So that means if x times y gives us 4, right? There's different numbers that would give us 4, but if we want to be able to easily graph these points, the 1, 1 and the -1, -1, where will they move to with a stretch? We want these values to be equal to each other. So the value for both x and y would be 2, right? 2 squared is 4, or 2 times 2 gives us 4. So we're basically going to take the square root of the a value, and that's gives us the new set of coordinates that we're going to move those points to. So what would that look like on the graph? Let's start with 1, 1. We're going to move it on a diagonal out to 2, 2. Okay, there's what our stretch looks like. Same thing for the -1, -1 point. We're going to move it on a diagonal out to -2, -2. Now our asymptotes are not going to change. They're going to remain on the x and y axis. So if we draw in the curve, it looks very similar, except it doesn't have quite as sharp or pronounced of a bend, right, as it comes and makes that turn from one asymptote to another. So the larger the stretch value, right, the more gentle or larger of a curve we're going to see in the graph. So that's what a stretch looks like. Now, what about a reflection, right? Notice we have a negative now for our a value. So we put in our parent function again. And this time, a reflection just says we're going to take whatever the distance is above the x-axis and reflect it that same distance below. So -1 or 1, 1 becomes 1, -1, and -1, -1 moves up to -1, +1, and then we can draw in our branches. So we're taking the entire branch, right, and just reflecting it around the x-axis. All right, let's look at our h value, right? Here, let's put the parent function in again. We're going to do the same thing each time. And we have an h value of 2, so a +2, which means, again, because of the negative sign in the form of the family function, we're going to move the opposite direction. So we want to shift everything to the left. Now, what is going to move? Well, we're going to move the vertical asymptote and the 2 reference points. So when we have a horizontal shift, the vertical asymptote will move. So let's do that. Let's move the asymptote first 2 to the left, and then we'll move these 2 reference points, also 2 to the left. The horizontal asymptote on the x-axis remains the same. And now we can draw in our new branches. So they have the same shape, right? No stretch or shrink, but everything's been shifted to the left. How about a vertical, right? So we start with our parent function, but now we have a positive 3, which means we're going to translate everything up, including this time the horizontal asymptote. So let's move the horizontal asymptote up 3, and then we'll move our reference point, both reference points, and then draw in the new branches. So everything just moved up 3, including the horizontal asymptote. Vertical asymptote just remains the same, right? You could say we slide it up and down the y-axis, but it's not going to change the appearance of that. All right, let's try a few more for practice here, and then we'll wrap this up. This is really just what we're doing in the lesson today. So we have y equals 9 over x. What type of transformation are we applying? Well, we have an a value, right? Our a value, let's put our parent function in. A value is 9, so the square root of that, right, would be 3. So we're going to stretch our graph out, our branch out from 1, 1 to 3, 3. Same thing from -1, -1 to -3, -3. So now we draw our branches in, and notice much more gentle curve, not a very sharp bend, the larger that a value. All right, let's try another one here, -16. So we have two things going on. The absolute value is greater than 1, so we have a stretch, but we do have a negative sign, so that's going to be a reflection. So we're going to do those two things. We're going to stretch these out to 4, 4, right, square root of 16, and then we're going to reflect it. So let's go out to 4, 4, and then reflect it around the x-axis. Same thing for our other reference point. Stretch it out to -4, -4, and then reflect it around the x-axis. And now we can draw our branches in. All right, let's try this one. 1 over x plus 4. See if you can just identify what the transformation is and what that would do to the final graph. All right, so 1 over x, put our parent function in there. Our h value is a positive 4. That's a typo there. It should be positive 4, which means we're going to move to the left. So we're going to move our asymptote to the left and our two reference points. And now we can draw in the branches. Everything shift to the left by 4. Here's a -3. That's our k value. So in this case, the horizontal asymptote moves down 3 along with our two reference points. So you can see it's really important to kind of picture where the new asymptote location will be, because that helps us to picture what the branches will look like. All right, let's do one where we have two transformations, both a horizontal and a vertical here. So we have a positive 4, that's going to be our k value, so we're going to go up 4, and we have a -3, which means 3 to the right. So we go up 4 with the horizontal axis. We're going to go 3 to the right with the vertical axis, or asymptote rather. And then we're going to move this point up 4 and over 3. And notice it kind of winds up in the correct place relative to the new asymptotes. Same thing with our other reference point, up 4 and over 3. And now we can draw in our branches. Okay, I think this is the last one here. We got a lot going on. We got a stretch with 16, a horizontal and a vertical. So let's see what this would all look like. So let's apply these. First thing we're going to do is our vertical shift down 2, horizontal shift 3 to the left. And then we're going to move these points right out to their stretched value, but then shift them by the horizontal and vertical components. So down 3 and over 2. And it turns out you could do them in either order. You'd still wind up in the same place. Do the same thing for our other reference point. Apply the stretch. We're going to go down 2, and we're going to go 3 to the left. So now we can draw in our branches. All right, that's about as tricky as it gets. So We know what the graph of the parent function looks like. Those two reference points creates two branches with two asymptotes, a vertical and a horizontal. And then we once again are applying these same transformations to those parent functions, stretch or shrink, reflection, and a vertical or horizontal translation. All right, that's it for the lesson.